Hello, ladies and gentlemen. Mr. Dorfler here for your daily dose of Dorfler. If you don't know, that's what I'm now calling my videos, the daily dose of Dorfler. I mean, why not? Come on. Anyway, got some video issues going on here. All right. So we have finished section or chapter 15, I should say. We got one more chapter to do before we can call it a wrap on the first semester, okay? Before we get into the notes, just make a general announcement that I will continue to be using Plan Book for your daily and weekly scheduling of material. So please take a look at that. I won't always be posting on Classroom what you can expect to do today. I think we've been doing this long enough this semester that you should have it down pretty well that you need to check Classroom, check your email, and check Plan Book or whatever other software that your teachers might be using to convey what is expected of you on that day, later that week. Okay, we got 3 more weeks to really hit this out of the park here. Make sure you end on a high note. Keep your grades up. Okay, now we're going to be doing these videos over content in the same fashion as if you would be in class. Okay, we're not going to sit there and do it one section at a time. It's just too much. Okay, so we're going to do exactly how I intended it to be in class, so you don't sit there and get burnt out on it. All right. So along with this video, I will also be attaching and posting the fill in the blank notes for you to follow along with. Okay. So I think that's all I have to say. Okay. Let's talk about it. Last chapter, we talked about waves, okay? Various types of waves and how they require a medium, with the exception of electromagnetic waves. Now we're going to be talking about sound and light waves for the most part in this chapter, okay? They follow a very similar concept as the waves that we saw in chapter 15, but we get to add a little more spice to it, if you will. So let's talk about sound right now. So the basic principles of sound. Sound is a longitudinal wave that is caused by vibrations and that travels through a material medium. Particles in a medium vibrate in the same direction as the sound waves travel. So that is basically the definition of a longitudinal wave. Okay, the particles are going to go in the same direction as that wave travels. Okay. Sound waves are caused by vibrations and carry energy through a medium, much like what we saw with the water waves. Sound waves that occur in air spread out in all directions away from the source. That's why when you are behind somebody and somebody that's in front of you is talking, you can still hear them because their sound waves are going basically in 360 degrees around them. It may not be as loud as it would be if you were standing in front of them because that is the direction in which they are speaking, but it is going all around, okay? If we look at a beating drum and the sound that is produced by that beating drum, when the drum is struck, that drum head is going to vibrate up and down. And this causes a series of compressions and rarefactions created in the air as it repeatedly moves up and down, okay? The drum head moving upwards is going to compress the air, and while the drum head is moving back down, it creates a region of lower pressure. This is where rarefactions occur. Again, it's supposed to be rarefactions down here, not refractions, rarefactions. So this is an interesting part about waves in general, but particularly sound waves. The speed of sound depends on a few things: the temperature at which the sound is being produced, and the material through which the wave travels through. So as we see an increase in temperature, the particles tend to move faster and will then collide more often. When we have an increase in speed and number of collisions that the particles have, it causes the sound waves to travel faster. Now, if we look down here, let's just look at the air in general. When we have air at 0 degrees Celsius, so freezing, the speed of sound is 331 meters per second. But as we warm up, say to 25 degrees Celsius, which is typically room temperature, we have 346 meters per second. At 100 degrees Celsius, 386 meters per second. So as we get warmer, they move faster. What's also interesting right now is this is kind of a long-term experiment, but if you were to compare the noises you hear outside between summer and winter, you will notice that the daily sounds seem to be louder in the summer than they do in winter. Winter kind of seems muffled. You don't necessarily hear things that are as far off as we used to, and that's all because of the air temperature. As the air temperature outside cools down, it does not allow for sound to travel as far when it's chilly. So that's why everything seems to be much quieter and a little more peaceful and serene, if you will, when it comes time for the weather to cool off. So the other thing is the medium. Okay, the medium a sound wave travels through is also going to help determine the speed at which the particles transmit the motion of the sound waves. In a gas medium, the particles are going to be spread over a great distance. This is going to cause vibrations of sound waves to be transferred from one particle to the next a little more slowly because they have a farther distance to travel between particles, relatively speaking. Again, at sea level, at room temperature is 346 meters per second. We just spoke about that in the last slide. But liquids and solid mediums, okay? Here in liquids and solids, the particles are going to be much closer together, and this is going to cause vibrations of sound waves to usually be transferred more rapidly from one particle to the next because they have less of a distance to travel compared to gases. But it does also depend on the molecular structure of the solid compound. We have situations where rubber is actually going to dampen the speed of a sound wave, okay? Or there also may be certain foams that are going to dampen. That's why if you see any recording studios or whatever, they typically will put, some sort of insulating material that is going to help slow down that sound wave. Now, we talk about intensity of the sound. It goes along with what we saw in chapter 15 with the intensity of waves in general, okay? The intensity is defined as the rate at which sound wave transmits energy through a given medium. It depends on the amplitude of the sound wave as well as the distance from the source of the sound. The loudness of the sound depends greatly on the energy contained in the waves. So the greater the intensity, the louder the sound wave or the sound seems to be. Kind of makes sense, doesn't it? Relative intensity is the comparison of the intensity of a sound with the intensity of a threshold of hearing. We call this decibels, okay? You may have heard this term decibels before. But it's on a logarithmic scale. If we increase the intensity by 10 decibels, it means the sound seems about twice as loud. 0 decibels is the quietest sound that a human ear can hear, and about 120 decibels is known as the threshold of pain, which can cause hearing damage. That's why oftentimes, one of the big ones that I always talk about is mowing the lawns. I personally love mowing lawns. I've mowed lawns since I was a young kid, but for a long time, as I kind of got into my teen years, which a lot of you are in, I should say most of you, all of you are in, I didn't have the sound silencing headphones that seem to be everywhere on the market. We had super loud motors on our lawnmowers, and the only thing that we could do to compensate for the super loud mowers was to blast our headphones as loud as we could. Well, that doesn't make much sense, does it? Because the louder that I was trying to overcome the mower's motor, I was increasing the intensity, therefore the decibels put on my eardrums. So I was not doing myself any favors by cranking up the music. Although I do love loud music, I learned that, with the introduction of more available hearing protection, that you can save your ears. Like, for instance, I've got those big earmuffs that look like you're on a construction site. Well, the nice thing about those is they not only dampen the sound really well, but they're also Bluetooth Bluetooth connected, so I can connect my phone, still listen to music, but I don't have to crank it in order to compensate for the mower's engine. So I can save my hearing by both protecting it from the lawnmower itself and protecting it from not having to crank the music up full blast. Okay. I mean, there's a time and place, but you obviously don't want to have full blasting music right next to your ears. Bad. And we're not going to watch that video. The pitch of the sound, again, is another term that we've heard in chapter 15. It's the measure of how high or low a sound is perceived to be, depending on the frequency of the sound wave. When we have high pitches, it's got high frequencies or something that's going to vibrate extremely fast, like a string on a violin or air in a flute. Then we also have low pitches. This is where we have low frequencies and they have really slow vibrations, like a cello or air in a tuba. Again, the violin and the flute are much smaller instruments, therefore it's going to typically have a much quicker vibration. And a tuba and a cello are going to be much larger and typically have much slower vibrating sound waves. Humans can hear from sources that vibrates as slowly as 20 vibrations per second or 20 hertz, all the way up to 20,000 hertz. Then we have infrasound with slow vibrations of frequencies lower than 20 hertz that humans cannot hear. And ultrasound, any sound wave with frequencies higher than 20,000 hertz. So there are some animals who use either infrasound or ultrasound to help communicate or listen or speak to other animals of the same species. Now, if we focus our attention onto musical instruments, we have standing waves. Again, these are all terms that we've heard. Most instruments produce sound through vibration of strings, air columns, or membranes. All musical instruments use standing waves to produce sound. A flute's standing waves is formed from the column of air inside the flute, and by opening or closing holes in the flute changes the wavelength and frequency of those standing waves. Another example would be a guitar. When a guitar string is plucked, the sound waves vibrate toward the ends and reflect back towards the middle. We have nodes and antinodes. Again, nodes are the ends of the guitar string. Antinodes are the middle of the guitar string where the sound hole is. If we see here on an acoustic guitar, the sound hole is right here. On electric guitar is where the pickups will be. Pitch of this standing wave is adjusted by the placement of your fingers on the guitar string. Now, you're probably wondering, like, how does Mr. Dorfler know much about guitars? Well, I used to play quite a bit, but time kind of has gotten away from me, and there's other things I got to do now. So free time to play is few and far between anymore. So I'd like to get back into it at some point. Another term is resonance, is a phenomenon that occurs when two objects naturally vibrate at the same frequency. And this occurs when forced vibrations are equal or have same frequencies as natural frequencies. Forced vibrations are vibrations that occur as response to the movement of an object, and natural frequency is specific frequencies of an object that is likely to vibrate at. The natural frequency, of an object depends on the shape, the size, the mass, and the material from which it is made from. Guitar string being plucked. As the string is plucked, the bridge and body of guitar vibrates. These are forced vibrations. The specific frequencies at which guitar string, if I can move this here, is most likely to vibrate is the guitar's natural frequency. It's going to do that again. Okay. Sorry about this. This happens every once in a while. Oh. Going to load? All right. Well, we'll go back to this. We'll do it this way. So the specific frequencies down here at the very bottom at which the guitar string is most likely to vibrate is the guitar's natural frequencies. I'm not certain why this will not. There we go. Oh, too little, too late. Anyway, like I said, these videos will go somewhat fast. You can watch these at slower speeds. You can even watch them at faster speeds, or you can even pause it. You have the power to do so. If you miss something, make sure that you get it paused and you make sure you get everything jotted down. Now, tomorrow we will take a short discussion on section 1, and I'll be posting your homework tomorrow with the video. So We're going to call it a day on these notes. And again, if you have any questions, feel free to hit myself up or Mr. Hampton. We, again, will be posting the notes to you so you can get them and use them. Okay, that's all I got to say. Anyway, have a great day, everybody. We'll see you tomorrow.